In today's lecture, we'll be discussing underlying processes in classical conditioning. So what is actually going on behind the scenes when classical conditioning is taking place? And there are a few different theories about what's going on. And the first is the stimulus substitution theory. And this was developed by Pavlov. And according to this theory, the conditioned stimulus acts as a substitute for the unconditioned stimulus. So the neutral stimulus and the unconditioned stimulus, through being paired together, become so closely associated that when that neutral stimulus becomes a conditioned stimulus, it takes on the properties of the unconditioned stimulus. And support for this theory is found in the fact that if you pair, for example, a light with meat, the dog or the organism who is being conditioned will sometimes go and lick the light, showing that the light is acting as a substitute for the meat and the dog is reacting to the meat and the light in the same way. Now, if this theory is true, we predict that the conditioned response and the unconditioned response would be the same or very, very similar. So if the conditioned stimulus and the unconditioned stimulus are acting as substitutes for one another, we would predict that the unconditioned response and the conditioned response would be the same. But we know that this is not always true. For example, if a tone is paired with a shock, a mouse will jump in reaction to the shock, but he'll freeze in reaction to the tone. So that conditioned response and unconditioned response are not always the same. Now, the fact that the unconditioned response and the conditioned response are not always the same can be explained by a different theory, the preparatory response theory. According to this theory, the purpose of the conditioned response is to ready the organism for the occurrence of the unconditioned stimulus. So remember that our conditioned stimulus predicts the occurrence of the unconditioned stimulus. And so the conditioned response that follows that conditioned stimulus is to ready the organism for the occurrence of the unconditioned stimulus. So if you take Pavlov's example, the conditioned response of salivation is to prepare the animal for the presentation of the food. So the conditioned stimulus of the bell brings about the conditioned response of salivation, and the purpose of that conditioned response is to ready the organism for the presentation of the meat, which is the unconditioned stimulus. So this preparatory response theory can explain the fact that if you pair a tone with a shock, a rat or a mouse will jump when the shock is presented, but once it gets conditioned to the tone, it will freeze in response to the tone rather than jumping. And this is explained by the fact that a rat or a mouse's reaction to having a predator there, to being attacked by a predator, is to jump, to try to flee the predator. But their response to seeing a predator approaching or sensing a predator is to freeze and try to sort of make itself invisible so it can't be detected by the predator. So the rat reacts to the shock as if it's a predator, it jumps away, and it reacts to the tone by freezing as if it predicts that a predator is coming. So this suggests that the purpose of the conditioned response, the freezing, is to prepare itself for the appearance of the predator, which is the unconditioned stimulus. So according to this theory, the unconditioned response and the conditioned response can be quite different from one another. They don't have to be the same. Now, the compensatory response model is an example of a preparatory response. And it's a preparatory response in which the US and the CS produce opposite responses. So the unconditioned response and the conditioned response are not only different from each other, they are opposites. And this explains some drug reactions. Now, this compensatory response model is very similar to the opponent process theory of emotion that we discussed in a previous lecture. So refresh your memory, that theory says that a stimulus produces two different responses. First, the A process, and that A process is a direct response to the stimulus. It also produces the B process, and the B process is an opposite response to the A process. And the purpose of that B response or B process is to try to bring about equilibrium or homeostasis. Okay, so how does the compensatory response model relate to drug reactions? So take, for example, if you have a heroin user. The heroin-related cues would be the neutral stimuli. So these could be things like the people that the person uses heroin around, maybe the room or the location where the drug is used. It can be the side of the needle, the side of the spoon, the side of a lighter. So any cues that that person has associated with the use of heroin would be neutral stimuli. Heroin or the use of heroin would be the unconditioned stimulus, and the unconditioned response related to that unconditioned stimulus would be a decrease in blood pressure. So using heroin brings about a decrease in blood pressure. Over time, through associating those heroin cues with the use of heroin-related cues become conditioned stimuli, and these stimuli bring about the opposite response. So the conditioned response will be an increase in blood pressure. So in this example, the unconditioned response and the conditioned responses are opposites. So going back to that opponent process theory, so heroin is the unconditioned stimulus. The A process, that's the result of that heroin use, is the decrease in blood pressure. So you use heroin, it decreases your blood pressure. That decrease in blood pressure, the A process, will bring about the B process, which is the opposite process. So that's an increase in blood pressure to try to equal out or combat that decrease in blood pressure. So once a person who uses heroin has associated those heroin-related cues with the use of heroin and the decrease in blood pressure, the body's response to seeing those cues will be to increase the blood pressure, to try to prepare itself for that decrease in blood pressure. So think back to that preparatory response theory. The purpose of the conditioned response of the increase in blood pressure is to prepare that person for the presentation of the US. So the body prepares itself by increasing the blood pressure to try to maintain homeostasis once the heroin, the US, is introduced, which will then decrease the blood pressure. So this compensatory response model has implications for drug addictions. So let's again take this heroin example. If all the cues related to the use of heroin are your neutral stimuli, and heroin use brings about, let's say, a sense of relaxation. So again, the heroin-related cues are the neutral stimuli, heroin is the US, and in this case, the unconditioned response to heroin use is relaxation. Okay. So over time, once those, the NS and the US are associated, the NS becomes a CS, so now the heroin-related cues are conditioned stimuli. That will bring about the opposite response from the heroin. So the heroin-related cues will bring about agitation. So remember, if heroin brings about relaxation, the heroin-related cues will now bring about a sense of agitation. So when that person is faced with those heroin-related cues, they'll feel very agitated. They'll feel very keyed up. And remember, the purpose of that conditioned response is to prepare them for the heroin, which will then make them feel relaxed. But when they're faced with those cues, when they're around the people they use heroin with, the room where they use heroin, the needle, the spoon, they begin to feel very, very agitated. And people tend to associate that feeling of agitation as drug craving. So I need this drug to calm myself down. And so you have that kind of cycle of addiction where all the cues that you associate with the drug bring about agitation. The way to calm that agitation is to introduce the unconditioned stimulus or engage in that drug use. It also has implications for drug tolerance. If being around the cues you associate with drug use, in this case, increase your blood pressure, you then can use more drugs. You have a tolerance for the drug because just being around those cues gives you the opposite response, which allows you to use more of the drug because your body is not starting from a balanced state. It's starting from a state of increased blood pressure, which allows you to use more of the drug. And this also can influence drug overdoses. So let's say a person uses heroin in the same location time and time again. That location has become a conditioned stimulus, which increases their blood pressure, which then allows them to use more of the drug. And then they go to a different location and use the drug. That new location is not a conditioned stimulus. That new location does not bring about an increase in blood pressure because there's no learning associated with that new place. They use the same amount of the drug that they have in a different location, and because they don't have that increased blood pressure conditioned response, they take the same amount of the drug and it decreases their blood pressure so significantly that they have a drug overdose simply because location that didn't bring about the conditioned response of of an increase in blood pressure. So this can play heavily into a lot of drug reactions. And so the last theory that we'll talk about as an underlying process in classical conditioning is the Rescorla-Wagner theory. And according to this theory, a given unconditioned stimulus can support only so much conditioning, and this amount of conditioning must be distributed among the various conditioned stimuli that are present. So basically, you can think about this in terms of an unconditioned stimulus only has so much value. Meat only produces so much salivation. A breakup produces only so much sadness. Food poisoning produces only so much nausea. And those values have to be distributed among all the conditioned stimuli that are present when that unconditioned stimulus is presented. We talked about earlier, a stronger unconditioned stimulus will support more conditioning than a weaker unconditioned stimulus. So for example, if a steak produces 10 drops of saliva and dog food produces 5 drops of saliva, a conditioned stimulus that is associated with that steak can only ever produce 10 drops of saliva. A conditioned stimulus that's associated with the dog food can only ever produce 5 drops of saliva. So moving down to our formula here, let's say you have a tone that has an associative value of 0. So the V is associative value, meaning that it's a neutral stimulus. It produces no response, so the value is 0. You pair that with an unconditioned stimulus of a steak, and the steak has a max associative value of 10. So that would be it produces 10 drops of salivation. If you pair the tone and the steak together over and over, the tone can only ever have an associative value of 10. That's the maximum associative value that it can have, because it can never produce more salivation than the steak produced. So the conditioned stimulus can never have a stronger or a higher associative value than the unconditioned stimulus with which it was associated. So think about that little graph of the acquisition phase. When you reach that optimal level on that acquisition chart to where as much learning as possible can take place, at that point, the tone can only ever have as much associative value as the steak had. So then we take a compound stimulus, like a tone and a light. The tone and the light in the beginning are neutral, so they have an associative value of 0. Pair it with the steak that has an associative or a maximum associative value of 10. Steak brings about 10 drops of salivation. Through pairing the tone and the light and the steak, at max, the tone and the light can take on an associative value of 10. Again, that's the max value of the steak. So the conditioned stimuli that were paired with it can only ever take on as much associative value as that unconditioned stimulus had. So if the tone and the light, when paired together, have an associative value of 10, if you look at each one individually, their associative values together can never exceed 10. So for example, the tone might have an associative value of 6, and the light might have an associative value of 4. They could have an associative value of 5 each. They could have an associative value of 1 has 7, 1 has 3. But we know that individually they can never have a value that exceeds 10 because they took on the value of the steak. And so since the steak had a max value of 10, they can never exceed that. Now, if one part of the compound stimulus has a higher associative value than the other, we know that that part of the compound stimulus is more salient. It's the one that stands out more. And so the one that stands out more takes on more associative value. And so that explains overshadowing that we discussed last week. So if you have a compound stimulus and there's one part of that compound stimulus that's more salient, that's going to take on more associative value than the other parts of that compound stimulus. It also explains blocking, which we discussed last week. So let's say, looking back at that top equation, if you have a tone that has an associative value of 0, is paired with a steak that has a value of 10, you pair those enough times until the tone takes on a value of 10. So it's absorbed all the associative value of the steak. If you were then to pair that tone with the light and the steak, and you were to then present the tone alone, it already has a value of 10. So the tone would produce 10 drops of saliva and have a value of 10. That light would keep an associative value of 0, because all of the learning associated with that steak, all of the salivation that the steak could produce, has been taken on by the tone. Since it has a value of 10, there's no associative value, there's no learning left for the light. So the light would not bring about any salivation. So that would represent blocking that we discussed last week.